Okay, thank you all. So I'm going to be talking about a theme that involves the atmosphere. Activities related to this have gone on in various arenas for some time at UCSD, and a list of people who've recently come together to discuss this, mostly in a different context than this workshop is given here. There are others that do related things, and this list is not meant to be exhaustive. I think you'll see there are many other people that will have tie into what we do here. So I think we all recognize that the atmosphere is a precious resource, it's a fragile resource, and it's one that demands very careful stewardship. It's not very different from land resources or water resources in terms of the societal value, but the challenges are different, mainly because the air so freely moves around from city to city, from county to county, from country to country, even from continent to continent. Examples of problems that relate to this are the buildup of greenhouse gases in the atmosphere and global warming. There are also regional issues involving air quality, particulates, health, water resources even. In every case, doing something about this, that is exercising responsible stewardship, requires understanding and regulating emissions of various agents that are harming the atmosphere. Now, they're both political and technological challenges to emissions control. You can see this, an example of this in the context of greenhouse gases. Suppose you want to negotiate a treaty to reduce greenhouse gas emissions between countries. Well, there has to be an element of trust. You have to trust that your partner is cutting the emissions along with your cutting emissions. How do you know that's happening? You need a verification mechanism. There's a good analogy here with test ban regulations that went on, that the implementation of test ban treaties required and went hand in hand with technologies for actually verifying through seismic methods. There's also a need for accurate accounting for instruments like cap and trade for regulating emissions, so that you know if you cut emissions by a certain amount, or you claim that you do, it actually happened, because it's credible with a monetary value. Now, for practical and historical reasons, the main ways that people have accounted for emissions is what you might call a bottom-up approach, where you tally activities that relate to emissions, and you have emissions factors for various compounds or chemical species that relate to those, and you come up with a budget. These kind of approaches are critical for regulating industry because they keep track of their practices, so you have a handle. They're also the basis for which emissions accounting is done, for example, at the UN Framework Convention of Climate Change, where countries report their emissions. These are so-called bottom-up approaches. The problem here is that these approaches are tricky to know if you got right. They're prone to being falsified, and it's very possible that there are processes that are emitting these species that have overlooked, or emissions factors may be wrong. You may not know how much every cow actually emits, and maybe the cows in India don't emit the same amount as the cows in the US. So an alternative approach to this, which is what we've been focusing on here, is to try to get a handle on emissions by direct observation. Now, what this shows here is a simulation of the plume of carbon dioxide coming from Los Angeles from fossil fuel emissions. You see this cloud here. Now, this is based on a bottom-up understanding of where the emissions are coming from, and it's predicting how the carbon dioxide drifts around in the atmosphere using a numerical model of how the atmosphere circulates. Now, the point is, you can't maybe verify all the emissions in detail, but one thing you can observe is this plume. You can put sensors out there and measure that plume. And if you do it in enough places and you have enough understanding of how the wind is circulating, you're in a position to actually verify that that emissions assessment was more or less correct. And you can refine on that. A good example of the failure of bottom-up here is shown. This is work coming from my colleague Ray Weiss on the emissions of carbon tetrafluoride, which is an extremely powerful greenhouse gas. The top black curve shows the annual accumulation in the atmosphere, that is the increment from year to year, measured from direct observations, and the various curves below show bottom-up assessments. The point here is these bottom-up assessments, in this case, were off by a factor of 2. Not a small amount if you're trying to accredit monetary value to this. Now, there have been a lot of rapid advances in the technology for measuring these kind of species. Many of them are going on here at UCSD, new sensor developments, new equipment for measuring aerosols, new equipment for measuring greenhouse gases. There's also a lot of interest in the policy aspects of this. There's engineering aspects, so there's a lot of related activities going on here. Now, to put this problem in a clearer focus, I'll give you an example of a recent development. So this is the planned and partly implemented network of a company called Earth Networks that's partnered with myself and Ray Weiss to put greenhouse gas measurement sensors around the U.S. Their idea was that they could sell information on emissions to various government bodies that needed to keep track of this. And they rolled out a fair amount of this, and it's gone forward to some extent. But two things more or less didn't work according to plan. The first is really on the policy side, and that was that they really didn't develop a market for this information in the way they thought. The other thing that didn't quite go according to plan is that the interpretive aspects of the atmospheric circulation, which required to go from the measurements to the actual emissions, really weren't ready for a turnkey application yet. In other words, this is still a problem that needs university research, it needs government lab research. It's a major challenge to actually pull all this information together. So this is still something that's going to need a decade of focus to actually get us where we need to be in terms of going between the measurements to the actual emissions. So I have two more slides here. I just want to mention that the applications here are broad. City, state, county level emissions assessment, impacts of new energy systems such as fracking and carbon capture. The emissions we care about could be on all different scales. Cities, they could be sub parts of a city, they could be industries. Urban air quality and public health, aerosols and photochemical smog. Turns out that rain also depends on aerosols, so that's another interesting application here involving water supply. And of course, there are strong legal and political aspects of this. There's strong programmatic synergies with what we do here. There's need for interfacing with geographical information systems, for satellite remote sensing products, advances in computational fluid mechanics, mathematical methods of data assimilation, sensor network developments, and there's actually strong analogies with understanding dispersion of tracers in the ocean. So that's really all I had to say. I just want to say that the group that's come together on this has really came together rather recently. We're excited about the possibility of working together on this, so it's an important area to keep track of. So thank you very much.
Well, as I understand it, we have mic runners, so we have 3 minutes for questions. If I could take the prerogative while you're thinking about your questions to ask the first one. I mean, the basic science behind quantifying sources of greenhouse gases and other pollutants, you couldn't get more serious than that, given the importance of climate change. And what I'm wondering is, to the extent that you have to do science communication, and I know you do a lot of it, does that kind of engagement actually enrich the science in any way? Because I think the basic science agenda has anything that you've done in terms of creating the network or thinking about the applications actually influenced and enriched your approach to doing the basic science?
Well, I mean, it does other things that are of great value. I mean, the science itself is rolling on the basis of nuts and bolts we're trying to turn the crank on. Certainly the receptiveness for what we do depends on communication. And so actually what's possible depends on receptiveness. You see that with Earth Networks struggling to find a market for it. So it gets very wrapped up in politics very quickly, and communication has a lot to do with informing the political process. So yes.
Is there any question? Are there any questions? If we could get the mic, because this is being recorded, so if you could please speak into the microphone, we'll get you.
You mentioned that we have about a decade, or you have about a decade ahead of you working on the sensor networks. Does that include time to work on policy change, or is that just getting the sensors in place and getting the programming and the data available?
Yeah, thanks for that question. What I meant to emphasize is I think we're already at a point where we can roll out sensors. The sensors are getting better. They're getting better all the time. So what we'd roll out in 10 years would be better than what we could roll out now. But Earth Networks is already doing that. What's going to take 10 years of development to get right is to go from a measurement of concentration to measuring this plume to figuring out how that relates to the actual emissions. That's an inverse problem. You have to sort of back calculate and optimize. And it's tricky. You got to get the winds right. You've got to get the mathematics right. You've got to put the sensors in the right place. That's what's still a big research problem.
That was time up. Okay. Next.
So thank you. Land resources or water resources in terms of the societal value, but the challenges are different, mainly because the air so free. Activities related to this have gone on in various arenas for some time at UCSD, and a list of people who've recently come together to discuss this. Okay, thank you all. So I'm going to be talking about a theme that involves the atmosphere. So I think we all recognize that the atmosphere is a precious resource, it's a fragile resource, and it's one that demands very careful stewardship. It's not very different from, in a different context than this workshop is given here. There are others that do related things, and this list is not meant to be exhaustive. I think you'll see there are many other people that will have tie into what we do here.